Hi, so today we're going to be looking at the energy in simple harmonic motion, right? So energy in simple harmonic motion, okay? So this is our last part for simple harmonic motion, right? Okay, so let's go about it. Um, so the basic idea, if we look at simple harmonic motion, uh, it's always good to look at good to look at pendulum as an example, right? So once again, pendulum is not a perfect example of simple harmonic motion. Okay, so I explained it in one of the last few videos where I talked about how in the simple harmonic motion the defining condition comes from a is negative omega squared x. Okay. Now, since a is negative omega squared x, what this means is that the acceleration must always be proportional to negative x. So essentially, this means that, if this is the equilibrium position, so let's say that the center position is the equilibrium position, then the entire force, the force that's acting on the object, always wants the object to go back to equilibrium. Okay? So the restoring force in simple harmonic motion always acts towards the equilibrium position. Now, what we mean by that is that, let's say if you have an object over here, so we learned before that if this angle is going to be theta, then the gravitational component in the x direction. So if this is gravity, this would be theta, right? And we ended up drawing the tilted axis. So if you have any doubts in this, then watch the previous video, okay? One of the few previous videos. Now, basically, we saw that the gravitational force acts in the x direction, right? But what we see over here, right, is that the acceleration is not proportional to negative x because the acceleration is happening at a tilt. It's happening at a tilt of theta, okay? So, in other words, this is not just one-dimensional motion in the x direction. You have the y dimension as well. So you don't get that tilt. You get that tilt, which is the main thing. Whereas if you have got a mass spring system, for example, if this is a mass spring system, then the mass is oscillating only in the x direction, and therefore the acceleration is proportional to negative x. Okay? And we looked at this one example in one of the previous videos where, if the bob was over here, then the net force, in this case the acceleration would be in this direction, and this acceleration would have been negative g sine of theta, right? And the main thing is that if this is 90 degrees, because you're going to the left, this angle would just be negative 90 degrees. Okay, because you're moving it towards the left. So this would just be like negative g sine of negative theta. And the sine of negative theta, if you see, sine of negative theta is negative sine of theta. Okay, that's a trigonometric identity. So therefore the acceleration is positive g sine theta, which would be acting at this direction. And the main idea you see over here is that the acceleration must be proportional to the negative x direction. But in this case, as we can see, the acceleration at this point, it's acting vertically downwards, okay? So that's why the acceleration is not acting entirely in the x direction. You get a tilt that happens. So that's why when you have a pendulum, it's not a perfect example of simple harmonic motion, okay? And so going back to our point, when we look at the energy in simple harmonic motion, we sort of visualize a pendulum because it's a good example. Like, we can visualize things much better using a pendulum. Okay. So, with that out of the way, we can look at the energy in SHM. Okay. So when you have the energy in simple harmonic motion, let's say that we make a plane over here, and in this case, let's say that this plane, so this is x, this is y, this is negative y, and this is negative x, right? So what we can see is that when the pendulum bob is at its maximum position, then right over here, this becomes max height, right? And you're going to see that these two heights on both positions will be the same, okay? So therefore, over here also, you're going to be getting a max height. And this height is just measured by the lowest point over here, okay? So when the pendulum is at its, so in this case, when the pendulum is going to be at its very edge, then it's going to have a max height. And we have learned in topic 2 that that in this case, you have this gravitational potential energy, which is mass times gravity times height, okay? So the pendulum goes to a certain height over here and it becomes mgh, okay? And so we can call this to be potential energy, right? And so let's say over here that you have a pendulum bob, okay? And the pendulum bob starts off at equilibrium and goes all the way to the right. Now, once it's all the way to the right, its velocity will become 0, right? Its velocity will be 0 and it will be at its max height. Then as it comes down, what's happening is that all of this potential energy is getting converted to kinetic energy. So at this equilibrium position, you're going to have maximum kinetic energy, okay? Then as it goes back up, its velocity will fall. And then suddenly it will rise, fall, rise, fall. So it would be like that. So let's say this is very fast and then slower and slower and slower. Slower and slower, slow, very fast, back slow, okay? So therefore, at the maximum height, you get potential energy that's being stored. And so this is mass times gravity times height. And then at the minimum height, all of that potential energy is getting converted to kinetic energy. So that's just 1/2 mv squared. So you get potential energy, and then that's converted into kinetic energy, okay? So therefore, in this case, this is just total mechanical energy. So this is all about topic 2, forces and motion. So therefore, in this case, total mechanical energy in a system, the total mechanical energy in a system is just given by the potential energy plus the kinetic energy, okay? Now, this potential energy can differ based on what we are looking at. When it comes to the pendulum, we were looking at gravitational potential energy, so that's mgh. But, when we're dealing with mass spring systems over here, then as we can see, this mass spring system, if we put it on the ground, we clearly see that the height is 0 meters, okay? So the potential energy in a mass spring system would not come from gravitational potential energy, right? It would rather, this would end up coming, so this would just end up coming from the, elastic potential energy, which is 1/2 kx squared, okay? So k is your spring constant and x is your extension. So spring constant, extension, okay? So what we see is that basically in simple harmonic motion, when you go to your max amplitude, when you're at the max amplitude, right? At the maximum amplitude, the velocity becomes 0, okay? At the maximum displacement from the mean position, the velocity becomes 0 meter per second. And then as soon as you get back to equilibrium, when you get back to equilibrium, the velocity becomes maximum, okay? So therefore, at your amplitude, you have maximum potential energy. And then at your equilibrium position, you have maximum kinetic energy, all right? Now, so for a mass spring system, if you look at the total kinetic energy, if you look at the total mechanical energy, then this is your total kinetic energy plus total potential energy, which is 1/2 mv squared plus 1/2 kx squared, okay? Now, that's how we would be writing this, right? Now, after this, there's a pretty important graph where we look at the energy in simple harmonic motion. So I think it's best to visualize this graph by looking at the pendulum, right? So let's put this. Let's make another diagram over here. Okay. So let's say we get this pendulum, right? Okay. So when we get this pendulum over here, once again we look at the pendulum bob, right? So if you have the pendulum bob, what you can see is that the gravitational potential energy goes like this. So the gravitational potential energy depends on the height, right? So as the height increases, the gravitational potential energy mgh should rise, right? Because mass is a constant, gravity is a constant, and so the gravitational potential energy depends on this variable h, which ends up varying. So therefore, as the h rises, gravitational potential energy rises. As it falls, gravitational potential energy falls. As it rises, gravitational potential energy rises. Okay? So in this case, what ends up happening is that if you draw this graph over here where you've got energy in joules, and then in this case you've got displacement, right? Now, when you get this idea of displacement, you would see that this displacement, the maximum displacement is at the amplitude. So to the right, you've got your maximum amplitude, and to the left, you've got your minimum amplitude. And as we saw, the gravitational potential energy depended on the height. So therefore, at this amplitude position, you would have maximum height, so maximum gravitational potential energy, and then it would be varying like this. Okay, so I'll draw it over here, and it will you can see it this way. So essentially, you would have this sort of thing. Oops. So it would be like this. Okay? That's how gravitational potential energy is going to be varying. So this is exactly like how the pendulum was moving. At the positive amplitude, you have max height. Then at the equilibrium position, so this is your equilibrium position, right? Okay, so at the equilibrium position, you have the minimum height, right? And then after that, the height ends up varying like this. Okay, so this graph shows your gravitational potential energy. Okay, now as we saw, kinetic energy at the maximum height, the velocity was 0. Okay, so the velocity is 0 at the amplitude, which is precisely why the kinetic energy at those points is simply 0. Okay, so the kinetic energy at these points becomes 0, right? And what we can see over here is that the kinetic energy is maximum at equilibrium. Okay, so that's why your kinetic energy would have the same maximum as a gravitational potential energy. So the kinetic energy is maximum at the equilibrium, and it's 0 at the amplitudes. Okay, so therefore the kinetic energy will move this way, right? That's how the kinetic energy is going to go. It's minimum at the amplitudes and maximum at the equilibrium position. Now, as we saw, the kinetic energy plus your potential energy is equal to your total energy. Okay, so if you want to graph the total energy, right, all we simply do is that we add up the individual points. So at the amplitude, the kinetic energy is 0, the gravitational potential energy is mgh. So therefore, if you add these 2 points, you get something like this. At the equilibrium position, the gravitational potential energy is 0, the kinetic energy is maximum, so you get this. Similarly, at positive amplitude, kinetic energy is 0, gravitational potential energy is maximum, so you get this. If you take these 2 points and you end up adding the respective energy values on the y-axis, you will get this. Okay? So if you add them up, you get this straight line, which basically states that the total energy in a simple harmonic motion system, the total energy remains constant. Okay? So it is only the kinetic energy and gravitational potential energy that varies, but the kinetic energy is going to stay constant. And this just tells you about the law of conservation of energy, right? So the law of conservation of energy would basically state that energy, right? So in this case, energy could neither be created nor can it be destroyed, but it can only be transformed from one form to another. So you're not making any new energy in the system. The energy is just transforming from gravitational potential energy to kinetic energy and vice versa. And so because of that, the energy in the system is staying constant, which is why there is conservation of energy. Okay? So that's basically how we look at this. Now the last thing we can see is that the kinetic energy plus the potential energy is the total energy. And this is also just equal to the maximum kinetic energy. This is the maximum kinetic energy, which is also equal to the maximum potential energy. So as you can see, the maximum potential energy over here is also equal to the total energy. The maximum kinetic energy at that point is equal to the total energy, which is this line, and so on. Okay? So this is the equation you get. Kinetic energy plus potential energy is total energy. And this is equal to the maximum kinetic energy and the maximum potential energy. Okay? And just remember that at the amplitudes, the velocity is 0. So at these maximum amplitudes, so as you can see, this is your amplitude, right? So at the amplitudes, the velocity becomes 0, right? And the gravitational potential energy is the highest. And in this case, the gravitational potential energy does not always have, in this case, the potential energy does not always have to be mgh, because in a mass spring system, you can have elastic potential energy, which is 1/2 kx square, right? And the intuitive way to think about this graph is you can just imagine a pendulum movement. So in this case, the gravitational potential energy in a pendulum depends on the height. So it's sort of like a pendulum is moving left to right, and you have got this variance of energy that's taking place. So like this. Okay? So if this is how the potential energy works, then the kinetic energy is sort of the complement or the opposite of that. And then once you add up both of these points, you get this total energy over here. Okay? Okay, so with that, we are done with simple harmonic motion, and we'll start looking at a few questions. Okay, all right, good luck.